Right, in this video we're going to introduce the planes in R3 space or 3D space. We're going to start by doing a recap of what we said in the previous videos about lines in 3D space. If this is our XYZ axis, and this is our straight line. We said we need one point through which the line goes, and we call that x naught, y naught, z naught. The position vector of this point is going to be a vector with the same components in the respective positions. So R naught is going to be the vector x naught, y naught, z naught. Then we said of the direction vector of this line. So imagine that the direction vector m is given by alpha, beta, gamma. Okay. Then any point, the position vector of any point x, y, z, which is this one here, it's going to be given by so from the origin we do the vector from 0 to x naught, y naught, so that's going to be r naught. Then we are going to multiply by a parameter t into the direction vector. So then, depending on how far this is from the x naught, y naught, and whether it's on to the right or to the left, that's going to determine the value of t. So if we're just talking about this point, then t is going to be 0. So of course the direction vector is going to be just some vector in the same direction as the line. So if you multiply it by 2, it becomes twice as long. So we said this is going to be the vector equation of that straight line. So this we can write, of course, in terms of the vector matrices. So it's going to be alpha, beta, and that's going to be gamma. Then we say from here we'll split this into the respective components, and this is going to give us x equals to x naught plus alpha t. So t here is our parameter, so t must be a real number. Y is going to be y naught plus beta t, and z is going to be z naught plus gamma t. So this first one is a vector equation. So this one is a vector form. This one is the parametric form. Then we said you can make, if you eliminate t here, you get what we call the symmetric form for the equation of a straight line. However, what we have already covered now is good enough for us to go to extend this to the idea of the equation of a plane in 3D space. So we are going to imagine that this is our plane here. Just for simplicity, we're going to take it to be horizontal. So this is our plane, which we're going to call pi. We are again going to imagine that on this plane we have got the point x0, y0, and z0 like before. And then we are going to imagine that there is a vector which we're going to call n, and this vector is perpendicular to this plane, so we call it the normal of the plane. So we're going to imagine that n is given by the vector a, b, c. Then we need two vectors in the plane that are not parallel to each other. Right, so in this case we need two direction vectors, both of which must be in the plane. So if we imagine that this is one direction vector, we are going to call it m1, and let's imagine its components are m11, m12, m13. So let me so that's one direction vector m1, the components m11, m12, m13. Then we need another direction vector. So for a plane we need two of them, which are not going to be parallel. So imagine, so this is m1, imagine this is m2. We are going to imagine the components of m2 are m21, m22, m23. Then similarly to this vector equation for the straight line, vector equation of this plane going to be given by r equals to r0, which is the position vector of this point on the plane, and then plus, let's use lambda m1 plus mu m2. So that's going to be the vector equation of the plane, where lambda and mu are real parameters. So plane is going to have two parameters in its vector equation. If we write out this in component form, so that's going to be x0, y0, z0 plus lambda m11, m12, m13 plus mu m21, m22, m23. So that's the vector equation. If we split this, then the x component will give us x equals to x0 plus lambda m11 plus mu m21. Y is going to be y0 lambda m12 mu to 2, z is going to be z naught plus lambda m13 mu m to 3, and so this is going to be the parametric form of the equation. So for a plane, we don't have that symmetric form where you eliminate these parameters. However, we do have something called the scalar equation. The scalar equation works as follows. So if you take any point on the plane, and let's call it x, y, z. Okay, so the position vector of this one is r naught. Position vector of this one, if you imagine this is our origin, is r, and this vector here is going to be r minus r naught. Okay, and that vector is in the plane. Now this vector, because it's in the plane, is going to be perpendicular to the normal vector. So that means r minus r naught dot n is going to be 0, because the dot product of two vectors that are perpendicular is equal to 0. However, r minus r naught we can write as x minus x naught, y minus y naught, z minus z naught. N is a, b, c. If we do this dot product, we're going to have a into x minus x naught plus b into y minus y naught plus c into z minus z naught equals to 0. Then we can write this as a x plus by plus cz, and then plus d, where d it's just going to be, so d, not b, where d is going to be negative ax naught minus by naught minus c z naught. You can see that from expanding these brackets here. This equation here is what we call the scalar equation of a straight line. It's the equation you are typically going to have come across when say doing Cramer's rule. So basically you got 2x minus y plus z equals to 0, or even equal to 7. This is an example of a scalar equation of a plane. Okay, so this is the scalar form of the equation. So there are three forms. So there's going to be the scalar form, it's going to be the parametric form, and there's going to be the vector form of the equation of a straight line. Now let's look at a few examples. Maybe we're going to do that in the next video.